wonderful lunch. And now the last session of this conference, of today and of this conference. We will have 4 presentations, 3 presentations and 1 discussion. Let's see. And it all will be about fuzzy from all the possible perspectives. The first one will be given by Ines Bula, and the title is Uncertainty in Idea Management with Elements of Game Theory. So, floor is yours.
Yeah, hello. I am Ines Bula from University of Latvia, and my thematic is about idea management. And this idea management is a system that helps to generate, develop, and implement ideas. And the one up stage of idea management process is acceptance, development, and reaction of ideas. Idea generator, for example, employees of company are we would have a single player who generally offers many ideas. Idea acceptor are the second player who makes a decision of each proposed ideas. We will develop a possible interpretation and solution for decision making from a game theory perspective. And first, some definition and the results from game theory. Game theory can be viewed as mathematical modeling of strategic interaction, making it one of most powerful analytical tools in economics, especially microeconomics, social science, and other science. And in this case is set of players. Each player I has a pure strategy activity set, SI. As result, player obtains a 5 who is index I, and the normal form game then is object that in for this set of players, set of strategies, and pi of functions. A strategy combination S1 star, S2 star, Sn star from all strategy sets is a Nash equilibrium if for any player I, and for each strategy this player utility or phi of functions value is greater or equal with phi of functions value in situation when Si remain with Se. Nash equilibrium is the most commonly used solution concept for non-cooperative games. But Nash equilibrium does not exist in all situations, and we look game in extensive form. We see in this slide figure 2 one situation, and extensive form games with complete information is a game with a set of players N, and G represents a direct graph without cycles, having the initial node x0, the set of nodes, position x, and z from x as a set of nodes directly following this node x. Now, and in this picture demonstrates the tree of such a game with the initial state x0, 2 players. The first player make movie in this first node x0. Had 2 movies S11 or S12, and second player make movies possible in nodes A or B, and um, player two has four movies, but that we consider as strategies, then for this player also is four strategies. In a game in extensive form, it's extremely important to distinguish between actions and strategies. Movies and strategies. An action is possible movie of player at the information set, and in this feature, player one has the actions only S11 and S11, and this is also for the strategies, but for player two, actions is four, but player has take actions at two nodes, A and B, so he comes of with a plan in advance of what he will do not do at each node if he gets her. He has four strategies, S21, S23. This means the first movie is in node A and S23 is in B. And so we have four strategies for second player. And strategy of player in extensive form game is list of actions, exactly one of each information set of that player. In game of complete information, extensive form solution can be found by backward induction. This means at all terminal nodes with five vectors are considered from the point of view of the second player. In this case, in the figure 2, at each node available to him, the second player, player 2 evaluates the movies that give us a greater payoff. Node it is S21 and B is S24. This means the player 1 has opportunity to achieve only the payoff vectors with payoffs for 4 and 2, 2. And since for the first player, first coordinate 4 is bigger as 2, player makes movies S1, 1. So we obtain the solution of game, Nash equilibrium. The first player make strategy S11, a second player makes strategy S21, S24. And this is Nash theorem. If any finite extensive form game gamma with complete information, there exists Nash equilibrium, at least one of solution can be obtained by backward induction. Game theory application to idea management. Idea management is generally a long time consuming process. Idea generators and idea acceptors can be considered as two players with possibly different opinions. And in simplest case, we consider player one that make only two ideas, and the second player, the idea acceptor, is to evaluate the created ideas. And the second player has only two actions, accepted ideas or rejected ideas. And we look at the case, here's the situation, the deferred ideas is considered as a case when an idea is accepted or rejected, but is not possible separately. Usually, the evolution is a number, for example, profit, but it can also be a moral certification expressed on some numerical scale, for example, between 0 and 1,000. It is quite logical that is both case if we apply it to idea management. The fail will be imprecise, and the best can be assessed from above and below. It is uncertain interval. As a result, we can write the pi as interval, and as see in this picture 3. Better interpretation of the data management model could be achieved with the extensive form game with complete information because then there exists at least one Nash equilibrium always. This we can find with backward induction. And this extensive for game 3 include time dynamics. Only when ideas are generated and pi is attached to them from the generator side, does the company management bank evaluating them and make a decision to accept or reject them. However, in classical game theory, things are different. In games with complete information, the game tree with all 5 factors is known to all players. Based on this information, the game begins. Player may one makes the first movie, then player 2 continue with his movie. Here, the generator, player 1, propose several ideas at the same time that is perform all possible action movies simultaneously. The idea generator needs to know what the payoff of each specific idea will be if it's accepted or rejected. We assume that the idea generator has calculated the possible minimum A and maximum B payoff of the idea, so the payoff can be interpreted with the interval from A with B. We assume that payoff of reaching the idea is minus B minus minus A. The idea acceptor, which can evaluate all ideas, we assume that the payoff of the reaction is 0. But the payoff of the acceptance movie is an interval CD, where the lower bound indicates the possible smallest payoff of this idea, and upper bound indicates the possible largest payoff of the idea from the side of the idea acceptor. The lower bound can be either positive or negative number. And which the we see on this example of such situation. In this big feature, player 2 has movies S21, S23 accepts idea, and S22 and S24 reject idea. If we are looking for Nash equilibrium in this game with backward induction, then we must be able to first compare the payoffs of layer 2 at nodes A and B. This means what is bigger, interval -1, 7 or 0, and -4, 3 interval and 0. We need to create an interval preference ordering. And we here give one variant of interval orders. In this case, we need also preferring what is bigger or smaller, this interval or 0 point. And so let's compare 0 and interval AB. In this case, interval is A smaller R/B strictly. In first situation, if 0 not belongs to interval, then 0 is bigger as interval. If 0 is bigger as endpoint B and is smaller, if 0 is less as first point A. See pictures I1 and 2. If 0 belongs this interval, then 0 is bigger as this interval. If absolute value from A is bigger as V, and in other case, if absolute value is less or equal B, 0 is less as interval A, B. If we compare two intervals A, B and C, D, then first situation, if intersect these intervals no, then AB is less RCD if B is less C. But in case when intersection is not empty set, empty set, yes, then we have four situations. In first case, box interval AB here and CD is this. In this case, C is greater as A and B greater as B. Then we say that interval CD is greater as interval A, B. In the second and third situation, we look that interval AB is sub-interval CD in both this situation, and then we look this absolute values distance between DB and AC. If this BD is greater as IC or equal, then we say that interval CD is greater as AB. And in second case, when this interval between CA is greater, then we say that interval AB is greater as CD. And both is equal if A is equal C and B equal D. And so if we look of our picture 4, then in this situation and in node A, second player shows movies between S21, S22 and air compare -1, 7, 0, then this is bigger than mode S21. And in this case, 0 is bigger as interval -4, 3. And this means at node x0, player 1 must show the largest of the values between 5, 8 and -6 being -3. And naturally that in this case, largest is 5, 8 and must make movie idea 1. As a result, a Nash equilibrium is obtained this pair of strategies with phi for first player phi 8 and for second interval -1 with 7. It should be noted that the decision making or determination of the Nash equilibrium occurs only after the idea generator has submitted all ideas for evaluation and evaluated them himself, after which the idea acceptor has evaluated all ideas, resulting in 3 of existence game 4 form. None of this decision can be made performing backward induction. In general case, any ideas are submitted. The game 3 is in we see in figure 5. This figure shows game 3 in which the generator offers n ideas, and each of the nodes IAE reviewed by the idea acceptor, making movies S21 accept or movie S22 reject. In general case, of many ideas are submitted, then the idea acceptor can also accept several ideas. With backward induction at node S0, the pairs of idea generator must be compared, and the largest pair among the accepted ideas must be found. With backward induction, at least one Nash equilibrium is found. more than one if the payouts are equal. If k ideas from n must be accepted, and k less n, then after finding the first Nash equilibrium, the branch that gives the first Nash equilibrium can be excluded from the game 3, as we see in this picture, for example, first idea, and search for Nash equilibrium in the remaining 3. In conclusion, theoretically, it is possible that the minimum payoff of all proposed ideas is so small, a negative number, that all ideas are rejected. In this case, the Nash equilibrium obtained by backward induction will be the one of the idea generator has evaluated with the smallest possible payoff. Then it is the largest payoff among the rejected ideas. So it is the worst idea from the idea generator side. To prevent such a situation for occurring, this decision-making scheme must be allow for repeated evolution or the use of repeat game. We have shown that the extinction form, extensive forms, the game can be used in the idea management system as a decision-making tool. However, the game tree must be created after the action occurred, and the decision must be made directly from the analysis of game 3, finding Nash equilibrium. And interesting to note that the opinion of the idea generators themselves about all the ideas they propose is important in making the final decision. Thank you.
Thank you for the presentation. We are exactly on time, so any short comments or questions? Okay, comments? Okay, if not, then thank you very much again. And now the discussion part to be given by Kamila Houšková and Mirko Navara, and the topic is independence of fuzzy events.
Good afternoon, ladies and gentlemen. We decided to present our joint work jointly as an experiment. And I'll start with some motivation. Okay, the decision to take the trip to the open air museum depended on the weather, but the weather did not depend on our decision. So this is a causal dependence, which is rather difficult to discover by statistical tools, even in classical logic. So I will not touch it. This is really a big problem. But definitely the dependence in the classical logic is a symmetric relation. And so is also the independence. So the winning of our indoor soccer team is independent of the weather, I hope. And also when the weather is independent of the soccer match. So these two events are independent. And what I want to emphasize is that also our not winning, the negation is independent of the weather. Of course, it's so, and we will see that it's not as simple in fuzzy logic and fuzzy set. So the independence has a clear formulation. For instance, this one, which I shall use, if you are used to say that the conditional probability is the unconditional probability, it's equivalent. And what I wanted to emphasize is that if you replace bi by its negation, you still have the same property by proof on a single line. So that's the classical situation. And now let's go to the fuzzification. So we shall start.
Okay, so this is the classical probability space. Can we maybe denote it a little differently as well?
Okay, we can. For instance, well, this is the standard definition of a sample space sigma algebra with subsets and probability measure defined by countable additivity. This is not much prepared for its fuzzification. So let's modify.
Okay, is it still the same?
Well, it is. Here we assume closeness under finite unions only, but taking monotonic limits, we get the same. And similarly for additivity, we can assume just finite additivity and preservation of limits, and that's equivalent. So let's use this definition.
Okay, well, can I exchange the union for intersection?
Well, why not? It's a dual, so and we have closeness under complement. Why not? Yes.
And how about the second condition? Can I rewrite it like this?
Well, there is equivalent in classical situation. What is the advantage?
Well, let's go to the.
Because we can avoid this difficult condition of disjointness, which causes troubles when fuzzified. So let's use this. So what is here is still the definition of a classical probability space, just rephrased in another way.
But we're at FSTA, maybe we should fuzzify it.
Okay, so we have a collection of fuzzy sets called a tribe for historical reasons. And you see that it literally repeats the definition on the left-hand side.
Okay, but like there's a general fuzzy conjunction and disjunction, so which one do we use?
Okay, that's to be specified more. So we need to complete this part, and okay, we can choose the Gödel operations, product, Lukasiewicz. Of course, the union will be induced by the dual T-norm. So we have a lot of choices. We have a lot of freedom. There must be some good answer, at least one. And what is important that Boolean elements, that means crisp sets, form a sigma algebra of subsets. So they behave classical, and we will need it. So please, BM will be the set of Boolean elements here. Okay. So we have this situation. We have sigma algebra type. We will specifically speak of Lukasiewicz types, where the Lukasiewicz operations are chosen. Boolean sigma algebras need not be set representable. They are somewhat outside this main line, and there are many other generalizations up to depot sets introduced for the first time here long ago. Okay, so the red structures are those which are representable by fuzzy sets. And now, preceding results, mainly by Butnario and Clement, show that roughly, under some mild assumptions and corrections, all elements of a tribe are fuzzy sets which are measurable with respect to the sigma algebra of crisp sets. Important fact. Because this allows us to introduce so-called probable integral measures. We can integrate the membership function with respect to a probability, classical probability, which is the restriction of the probability from the whole tribe. So we have, and in fact, almost all reasonable measures are of this kind, integral measures. That means each part contributes proportionally to its membership degree. Well, quite a natural idea expressed already by Zade, but without a precise support. What is an integral? What is the domain? What, and so on. Here it's made precise. The surprising fact is that only Frank T-norms and conorms are allowed. Otherwise, we don't have any integral measures and almost nothing. So another important notion is that of a partition of unity, which in Boolean algebra is a collection of mutually disjoint sets which cover the whole space.
And how does it look in tribes?
Well, but it requires a modification because being being disjoint in this strict sense is quite a rare situation. So instead of that, we switch to an equivalent formulation that one is below the complement of the other. Well, in classical case, the same here, it's a strong condition. Even more, we want the union of all sets but one be covered by the complement, by the missing element of that. So far, we are in classical situation. And now let's apply it to a tribe. So we need some fuzzy disjunction here of all elements but one, which occurs on the right hand side. And it should cover the whole. That means the fuzzy disjunction must be one, which is just a restrictive condition, as we'll see. An easy way how to say it is the spinning condition. The sum of all membership functions is one. That's easy, but that's allowed only until we have set representable events. That means in tribes, yes. If in Boolean sigma algebras, not, because we don't know what this sum is. So an important thing is refinements of partitions of unity. One partition is finer, see, and the other is closer. If each element of the closer one can be expressed as a union of the finer ones. And having two partitions, we want to have a joint refinement, which is finer than both. And in particular, it would be nice to have the closest joint refinement, which is, say, the simplest one among them. This is easy in the case of Boolean in the classical case. In Boolean algebra, any functions of unity have a canonical joint refinement. The closest one, which is simply done by the conjunctions. Well, now we are in this situation. So the sum of the probability values over partition of unity should be one. That's another way how to express additivity. Finite additivity. And for integral measures on type, this means that the fuzzy disjunction of the elements must be one up to set of measure 0. Okay? In particular, let's apply it to the two-element partition of unity A and then its complement. We obtain that, well, that's an axiom of probability, that A in disjunction with its complement must be one, which is not satisfied by many conjunctions. Almost only the Lukasiewicz one is a good suggestion. There are some other nilpotent ones, but we don't care. So let's assume that only the Lukasiewicz disjunction is considered here in order to have a chance to satisfy it. And now, what about the only the conjunction is to be done? Okay, we'll need independence of events. And two events are independent if they satisfy this usual condition of independence.
Well, which conjunction do we choose?
Well, we have a lot of options. So the right-hand side is clear. That's usual product. What is that? So several options have been tested, and we've found the following thing. For crisp events, of course, or if we switch to complements, it's equivalent, like I said in the beginning. For fuzzy events, regretfully not. So the fact that B is independent of A and B prime is dependent of A, what to do with that? So there are several ways out. One of them is take the product conjunction. That is nice. that satisfies this equivalence. That works. Another way is to change the definition of the independence and say that two events are strongly independent if all these four equations hold for combinations of elements and their complements. So this is strong independence, which is a stronger condition, and now it's equivalent for, of course, for any choice. So strong independence means that the sum over these elements should be 1 for integral measures. This means that the sum of membership values of these fuzzy conjunctions should be 1 up to measure 0. And that means this should be a partition of unity, which refines the partitions A and its complement, B and B its complement.
And is it always the case, or?
Regretfully. Well, I suggest, what about Gödel intersection? A Gödel conjunction here?
Well, obviously not, because in the middle it's way more than one. And we sum them all up.
Well, let's suggest the Lukashevich intersection.
Yeah, it's way less than one, so that's good
Bad.
either.
I would like to have Lukashevich operations. Okay, let's combine them, like Munich did, okay?
Okay.
Gödel, Lukashevich, Gödel, and it sums up to 1.
Yeah, but then it's not symmetric, so if you, yeah.
Yes, if we interchange B and its complement, you have something else. So. Well, take the product.
Okay, yeah, that works.
Yes, that works. That's the solution. And in fact, the only solution. So we need product types in order to have independence with good properties. But we needed also the Lukashevich operations.
Yeah, well, that's no issue because they're closed under Lukashevich.
Yes.
operations.
Utario and Clement have found a clever proof that if we have product operations, Lukashevich operations can be performed as well. Okay, good to know. So product types are in fact special case of Lukashevich types. And we have this situation. So in between sigma algebras and Lukashevich types, we have product types, which work well for introducing fuzzy probability. We have Boolean sigma algebras, which work also well. They have some common generalization, which is the topic of the next talk of my course. Thank you for your attention.
Okay, thank you very much for the presentation / discussion. Any questions, comments, remarks? Okay, thank you.
If you recall from my lecture on Tuesday, the history of preference structures and fuzzy preference structure, it's exactly the same story where we try to partition not a set, but a Cartesian product of A and A. It leads to the valuation property, which is behind the Frank equation, what we did with Janos Fodor. And you have freedom to define strict preference and difference with two different t-norms. But at the end, if they need to be the same, then product is the only way out. So you will lead again to the same thing. We have a lot of freedom, but at some point it leads to products. Even in an older story, it's just for historical reasons. I think it's one of the first joint things with Radko. If you define conditional possibility in a free way, use a t-norm and so on, but you still want the conditional possibility measure to be a possibility measure, then you get the same Bayesian rule. Product is the only way out. So my question, can you explain, can you give any intuition behind why product always pops up?
Oh, I'm a mathematician. For me, it says, okay, there is a proof that that's the only solution. But I would say it's quite natural. It's quite natural because it says that each part of the fuzzy set contributes proportionally to its membership, which is in fact a not surprising thing and not very encouraging for people to study fuzzy sets, because they could say, okay, this is so natural idea that I can skip all the stuff behind and say, okay, yes, I go this way. That's that we need the product, and we will bring more arguments later on for that.
More questions or comments? Okay. If not, let's thank once again. And we can continue in almost same topic, so it will be independence of fuzzy observables. Right.
Okay, thank you. Hello. And why we asked these questions, we saw that many papers successfully find fuzzy analogs for many classical big theorems, for example, the central limit theorem and the law of large numbers, using different definitions of fuzzy unions, intersections, independence, and joint distributions. How did they do it? Well, their assumptions were different, but the conclusion and the way of the proof were very similar. These results assume sequences of independent random variables, so independence plays a really key note here. Well, this is what you saw in the last structure. So for all the red structures, you can define the classical like theorems if you just have a product. Well, we've also looked at a common generalization of these, which is a sigma MV algebra. So let's remind us of the definition of a sigma MV algebra. It has two binary operations, Lukasiewicz conjunction negation, disjunction. Then you have like unary negation and two constants, 0 and 1. So the negation is convoluted, 0 equals 1 prime, and the binary operations, disjunction and conjunction, have neutral elements 0, 1 respectively. They are also commutative, associative, they satisfy De Morgan law and this last equation as well. And when we have a MV algebra is said to be sigma complete if its underlying lattice is also sigma complete. And an example of this is the standard MV algebra with the real unit interval with the Lukasiewicz operations, and it's a Lukasiewicz tribe of constant fuzzy set. Okay, so Lukasiewicz tribes are sigma MV algebras, but there are also sigma MV algebras which are not fuzzy set presentable, thus they are not tribes. So let's define the probability measure. It's normalized. It satisfies this condition, this form of additivity, and it preserves the monotonicity. And then partition of unity. Well, in sigma MV algebras, you also need a stronger form of or orthogonality than in Boolean sigma algebra, and it covers the same as it was in the tribe. Okay, in particular, A and A prime is a partition of unity. In tribes, a partition of unity could be defined by a single condition like this, but it has no meaning in non-set representable sigma and V algebras. In a sigma and V algebra, a probability measure satisfies that for all partitions of unity, their probability measure, the sum of their probability measures is equal to 1. Well, in Boolean algebra, partitions of unity have a canonical joint refinement, which is the coarsest one. However, in a MV algebra, this doesn't need to be a partition of unity. For example, for Lukashevich group and partitions of unity A and prime B prime, usually this is less than 1. So as we saw in the last lecture, in the middle, it's less than 1. Okay, so Mundici proved that partitions of unity have joint refinements, but neither a canonical nor the coarsest joint refinement. For example, these two expressions have joint refinements, but none of them is the coarsest joint refinement. The non-symmetric forms of elements of the joint refinement cause problems. In tribes, for this expression to form a partition of unity, the fuzzy conjunction needs to be a product. So let us extend the definition of a sigma MV algebra to product. It's a binary operation, it's commutative, associative, it has a neutral element of 1, and it also satisfies this last condition, which basically means the distributivity with respect to the operation that in Lukashevich type is called the truncated subtraction. An example of this structure is each product type. In an NV algebra with product, partitions of unity have canonical joint refinement, which is not the coarsest one. Well, a random variable on a type M. So that's a function f such that each preimage of a Borel set has to be in the type. It corresponds to a sigma homomorphism such that x of A is equal to the preimage of A, called an observable. An observable can be defined even if the event structure is not representable by fuzzy sets. And finally, we define the observable. An observable on sigma MV algebra is a sigma homomorphism, like this. Okay. And as we saw in the last slide, we can either, in fuzzy sets, we can either have basic independence or strong independence. And strong independence implies the basic one, but the basic one doesn't imply the strong one. Okay, well, let's see how the independence looks in observables. The independence to observables can be formulated as independence of xc and epsilon y or epsilon d, yd, like this for all Borel sets C and D. This applies also to the negations. So if I take x c prime, it's the same as the prime of xc, and the same with d. And if the observables are independent, then these xc and yd are strongly independent for all Borel sets. In the previous lecture, we saw that the strong independence is achieved only for the product. Then also, this is a partition, this equals 1, yeah, sums up to. In many papers, however, Gödel and Lukasiewicz conjunctions are used in the place of general ones in the definition of independence. However, this expression is not partition and of unity, and this doesn't have to always equal 1. The difference on both sides of probability of NAB, where NAB is this, and the condition of probability of NAB being equal to 0 is very strong, and it excludes most of the fuzziness of the model. So, for example, if we take strongly independent events on a tribe in this sense, then for all but one J, the events will be either 0 or 1. So this if yeah the classical theorems work well, but for these red structures. And let me conclude. We summarized many different definitions of independent and joint distributions on a unified platform. We recognized some errors in the sources. Some papers even ignore the events and define a joint random vector with the desired distribution, but without any relation between the events behind it. Some papers use independent, which without recognizing how restrictive they are. And then all fuzzy logical operations collapse and coincide with the product one up to a set of 0 measure. So it's really strong assumption. Thus we have a product and we cannot build a reasonable fuzzy probability theory without it. And thank you very much for your attention. Hope this talk was, yeah.
Okay, thank you very much for the presentation again. Any questions, comments?
Thank you for the questions. It was very interesting. I have a question on the use of the product on MV algebras. There is an alternative way to deal with product of elements of MV algebra, which is tensor product. It's not an operation, it's not an internal operation of the algebra, it's mathematical construction within the algebras. It behaves as a product, but it's not really the product operation. Can you consider that construction to deal with independence and conditional probability in this case?
Yeah. I'm not as familiar with tensor product.
The problem is what you mentioned. It's not an inner product. So we are going outside, and we did not say what the probabilities on that. So this would mean to introduce all into something bigger and extend to
Yeah, I think there is another
very different context.
there is anyway something could be interesting to consider, because the product to MV algebra is an MV algebra. So you actually don't get out of MV.
You don't get out from MV algebra.
You
Get out from the original one, which the probability was defined.
Yes, yes. And that's
difficult
that
to-
could be the interesting thing of extending the measure to another MV algebra. Still semi-simple, possibly, and then
Okay, ambitious plan. Thank you.
yeah.
Okay, more questions or comments?
I'm just curious in your definition of MV algebra with products. Is that product preserving some order? And if so, which one?
Yes, it behaves normally with respect to the order, and it's not our definition, it's that of Riechan and Mundici.
But it's not in the definition.
Well, this is the definition of a product in an MV algebra with
Yeah, so my question is, does from this follow that this operation is preserving some order?
Well, we did not mention it explicitly. MV algebras have an order, and it is order preserving. It's a multiple multiplication by it behaves like a multiplication by a non-negative constant, but having no set representation, neither a fuzzy set representation, this is the way out how to define this operation in an abstract way, not referring to anything else, but it is order preserving. Yes.
Can I have a second question very quickly? You mentioned fuzzy observables, but it's still for random variables. So if I look at fuzzy variables from Lotfizade's point of view, I'm in the context of possibility theory, where we have the notion of non-interactivity. Does this learn us something about that setting as well?
That's another direction what you mentioned.
I know.
The direction from the step from random variables to observables is in fact brought from quantum theory, where this discrepancy was recognized for the first time, that in fact Kolmogorov defined random variables in a real way, in the opposite way than the natural one. Yet it's difficult to explain to students who can easily imagine functions and so on. But in fact, the right definition of something like a random variable is that of an observable, as a mapping from the Borel sigma algebra to the structure, not vice versa, because there may be no points. So this is the situation in quantum logics, but this is also the situation in those structures like here, for instance, sigma MV algebras, which need not be set representable, neither fuzzy set representable. So you don't have points, but you still can define random variables in this opposite way, which doesn't mean that we fuzzify this notion. We just correct it and extend it to structures where it could not be defined in the
Apply the same approach to get fuzzy observables and non-interactive.
Still have time for questions.
Probably in previous lecture you have mentioned types based on rank connectives. They never appeared here. Does it mean that observables can be constructed only by means of Lukashevich product, or you can go also to slightly more general connectives, this Frank connectives?
Okay, Frank Tinoms would. So what remains are strict Frank Tinoms different from the product. Yes, they admit integral measures, but again, when you try to sum up and construct a joint refinement of distributions, you fail like in these pictures. Again, the sum will not be what we wanted. So there is just one case in the middle, that's the product, which has these properties. So sorry, they are excluded as well after this step.
Okay, we can discuss that.
Okay, I guess more questions during coffee break or football match at some point. Okay, thank you very much once again. And the last presentation of this session and today and the whole conference is given by Maria Slovinska, and the topic is alternative statistical moments under a Schokke integral framework.
Thanks for introduction. So today I will talk about alternative statistical moment and the Schokke integral framework. And this work was done together with my colleagues, my supervisor, Jozef Kiselák, Zuzka Ankovičová, and Milan Stiehlik. So statistical moments are fundamental tools for describing the properties of data distribution, such as location or variability. There exist several types of moment. Most commonly used are classical or standard additive moment, for example, mean or variance. Another category of moments are alternative moments, such as T moments, TL moments, or probability weight moments. And another category are shocked moments, which are generalization of standard classical moments, where a probability measure is replaced by fuzzy measure. And these moments allows more flexible representation of uncertainty or dependencies. And studying their relation can help understand their applicability and limitation. The results, which will be presented here, can be found in this article. So alternative moments have been developed to achieve greater robustness against outliers or to better capture behavior of some distribution. For example, L moments are computed according to this formula, where x is a quantile function and p is a Legendre polynomial. The L moments are trimmed L moments, where extreme values are removed to reduce influence of outliers. And they achieve great robustness, and they are computing according to this formula, where again x is a quantile function. T moments are obtained by transforming from standard scope moments. They also exist when a standard scope moment doesn't exist, and they are computed through this integral, where firstly we need to find t-score, which is computed according to this formula, where f is the density and eta is a mapping, which is given according to support of random variable. And another class are, for example, probability-weighted moments, which are widely used, for example, in quantile modeling or extreme values modeling. When we try to move on from additive standard moments to more generalized shocked moments, we need to move on from probability measure to more general set functions. So we work with a class of fuzzy measure, which is set function, which is grounded and monotone. More generalized is a set of non-monotonic measure, which are measures which are just grounded. By this notation, we will mean a set of all random variables. And when we have a random variable, we can build a survival function or a cumulative distribution function, which are building stone for defining a shocked integral. So here is the definition for shocked integral for a real valued random variable. So asymmetric shocked integral is computed as integral of positive pair with respect to fuzzy measure minus integral of negative pair with respect to a dual measure. It can be rewritten using survival functions, and asymmetric complementary shocked integral is computed as integral of positive pair with respect to dual measure minus integral of negative pair with respect to fuzzy measure. But it can be also rewritten using a cumulative distribution function. This definition, also with a definition of symmetric and symmetric complementary shocked integral, can be found in this article. I have it just these two because we mainly work with asymmetric shocked integral. In additive case, moments are based on expected values, and analogously, we can build shocked moments. So shocked expected value is defined as asymmetric shocked integral of the function g psi, or asymmetric complementary shocked integral of the function g psi. And we can also use symmetric or asymmetric complementary Schottky integral. And analogously, we can build central moments, and most common central moment is a Schottky variance. So Schottky variance is defined as a Schottky expectation of the squared deviation of Schottky expectation. For defining variance, we can also use another formula which is commonly used for computation in additive case as difference of second and squared first moment. So we get pseudo variance, and it's computed as Schottky expectation of the function of t squared minus square of Schottky expectation. It's obvious that in additive case, variant and pseudo variance coincide, but it's not true in general for fuzzy measures. And we were also interested in a relationship between Schottky variance and variance built on alternative moments, which will be presented in next part of presentation. To compute Schottky integral form definition, it's not always easy, so computational formulas are needed. When we have cumulative distribution function, we can build following random variable, which represent quantile, which is naturally non-decreasing. And when we have non-decreasing random variable, we can compute a Schottky integral as follows as a Riemann's integral. And this notation will be used for distorted Lebesgue measure. And for this measure of this formula simplifies to this computation. Schottky integral provide unifying framework for alternative moments types. When we choose appropriate distortion function, we can cover some alternative moments. For example, L moments. When we choose derivative of distortion equal to this polynomial, then first a Schottky moment encompasses any L moment. Or for the L moments, when we choose a derivative of distortion equal to this polynomial, then first Schottky moment covers any TL moment. Probability weight moment and the moments cannot be directly expressed in Schottky integral, since probability weight moments depends also on derivative of quantile function, and t moments depends also on derivative of transport quantile functions. Exact derivation and these formulas can be also found in the article. Although we can't cover t moments or probability weight moments directly to Schottky integral, we can define a functional which will cover these moments and also some other classical probability moments or characteristics. So define the following functional, where tau is a mapping for from the space of all quantile function to the space of all integrable function. And this operator can be, for example, differential types. When we choose following nonlinear operator, we get a probability weight moment. When we choose this operator, we get first t moment. And for the operator derivative, we get a range of data. And for other types, for example, when we choose operator's identity, we get classical mean value. And when we choose Dirac delta function, we get a classical median. Having introduced theoretical framework, let's compare a Schottky and L moment estimator on data. For heavy tail distribution, assume that we have a Pareto distribution where a random variable will be quantile function of a Pareto distribution with true parameters xm equal to 1 and alpha equal to 0.0. Sample of psi 3000 was generated and sorted, and the Schottky moment will be denoted as follows. Then from a computational formula, from theory, we can express Schottky moment using a distortion function as follows. And for k equal to 1 and for k equal to 2, we get the following
expression of shocked integral where b represent beta function. And from data, we can compute empirical shocked moment using this formula. We use one parameter power distortion as to the power of gamma, where gamma is a parameter. And then parameter estimated is obtained by solving the system. So values from data should be equal to theoretical values. We have a system of equation. And since we want to compare these shocked moments with L moments, we know from theory that L moments are equal to this for this distribution. And from data, we compute L moments according to these formulas. Then for each gamma 300 bootstrap resembles are drawn, and we compute the mean square error, bias, and variance. These tables summarize the result we obtained. We can see that the values we get from shocked estimator are much closer than the values that we get from L moment estimator. The best performing candidate was gamma equal to 0.6, where we get the smallest mean square error bias. And this example showed that choosing appropriate weighting or distortion can dramatically improve performance for heavy tail distribution. Another question we were interested in was the relationship between standard fuzzy moments and alternative moments, or define the condition when they're coincide. Since we want to cover general case, assume that U belongs to TTLOL, which represent TTLOL moments, and we want to find condition where alternative moment is equal to shocked moment. So again, we used a computational formula for shocked moment, and we get Fredholm integral equation, and suppose that solution is in that form, so derivative of m is equal to this expression, and then plug in this integral equation, we get this relation which connect alternative moment and classical moment. And using this expression, we formulate this theorem and find a feasible sets of parameters where alpha should satisfy this relation. We need convergence condition, and from previous relation, beta is equal to this. And since we want distortion function to be non-negative, quantile is non-negative, beta should be also non-negative. So this is the distortion function for which alternative moment will be equal to shocked moment, and it will hold when alternative moment is equal to this. In this example, we use a previous theorem and relations. So assume that we have uniform random variable. Then we know that the standard moment out in this form. We find from definition L moment, and then we found alpha parameter and beta. Since beta should be non-negative, then theta belongs to this interval. And we find the distortion function for which first two L moments will be equal to first two shocked moments. And since we need also convergence condition, feasible sets of parameters reduced to this. On the picture, in the picture we can see some distortion function for some values of parameters from feasible sets. We can see that all these distortion functions are non-decreasing and grounded, which we wanted. And another question which we were interested in was relationship between shocked variance and variance based on alternative moments. When first alternative moment is equal to 0, we cannot use previous relations since we lost some information about parameters. So we will try to find the distortion from directly from this integral equation.
we basically apply the same procedure as before. We assume that derivative of m is equal to this expression and plug in into integral equation, and we get this quadratic equation. We solve it for beta, and again we find feasible set of parameters where this inequality is from a previous quadratic equation, and we need also convergence condition. And these are the distortion function for equality of between Schocked pseudovariance and U variance. Again, using previous theorem is illustrated on this example. Again, we have uniform random variable. We computed t-score and first two t moments and t variance. Then we find beta, and according to this inequality, it will hold for these parameters. We can choose alpha, and then the interval will reduce to this. And so we get distortion function for which t variance will be equal to Schocked pseudovariance. And applying integral convergence condition, the limit of distortion function is equal to minus infi for alpha greater or equal than 1. So choosing alpha less than 1 is appropriate. And this condition and previous relation give us that feasible set of parameters is equal to this. Again, distortion function, I'll illustrate it in the picture where dotted lines represent the first solution and full line the second solution. To sum up, we compare Schocked moment and alternative moments. We studied the expressibility as a Schocked integral. We studied moment matching condition between Schocked and additive moment, and we illustrated result by examples and simulation. Thank you for your attention.
Okay, thank you, Micah, for the presentation. Are there any questions or comments?
We know that easy natural interpretation of classical media is a bounded balances distribution. Do you indicate such interpretation for Schocked-based expected value?
When we use fuzzy measure, we can emphasize some property we want. For example, when we want some criterion to be more important, we use a subadditive measure. And when we want less important, we use sub or super additive. Like it helps us to modify according to which criterion which we want to emphasize.
Okay, more questions?
Maybe it's a stupid or naive question. Classical moments we can find through application of Laplace transform, the moment generating function. Is there anything similar for these other moments or using Choquet integral, or doesn't that make sense?
I don't know. Maybe when I talk about defining some characteristics through this functional tau, maybe when we there use some integral operator, it could be possible. It can be question for other research. Yeah.
We haven't looked at it, but that's a nice, maybe future question for us. Okay, any more questions? If not, thanks once again, Maria. And with this, let me conclude the session. Thank you all for attending and enjoy this evening.